All right, hey everyone, and welcome back to our third lesson of this first part of the FRC curriculum. So welcome back. Today we're going to be talking about FRC assemblies. So this is going to be mostly just assemblies and different types of mechanisms that are applicable and generally used in FRC. The main idea of this lesson being to keep this whole thing sort of grounded in reality. Now, you may be using these things that I will be talking about for designs in the future. In fact, you probably will be, but mostly right now, it's just to sort of give you an idea of what first robots look like, what they can do, right, and how you build task-based mechanisms. Because that is something that sort of is confusing at first, and I just don't want to leave that up in the air. So again, just keeping it grounded in reality the whole time we do this. All right, so robots are made of mechanisms, which are assemblies of parts, like we discussed before. So many types of mechanisms exist, and they have to be designed around game task and game strategy. So, right, a mechanism is a mechanical subsystem that fulfills a game task. Like I said before in the previous presentation, that's literally what it does. That's the definition. So each mechanism will do something, and a lot of times those things are the same, even between different games, right? Even between different games. So climbers are something that's common, and they can be different depending on the game, whether you have to pull your robot up or push your robot up, or pull something down. But elevators and climbers are super common mechanisms. So those are some things that are really good to learn a lot about if you're interested in doing task-based mechanism design for a variety of FRC games in the future. Game pieces also usually need to be picked up and manipulated, right? So intakes exist, right? This is a mechanism on your robot that takes a game piece off of the field and turns it into something that's usable. And next we have game pieces that need to be moved, sorted, and or fired, right? So basically converted into points, which you can use elevators to move them up and down, arms to move them around, indexers to move them within the robot, and outtakes to convert them into points, right? Putting them out onto some sort of field, or onto some sort of field element, into some sort of goal, usually. So many of these varieties exist. But most importantly, the robot has to be able to drive and traverse the field, right? Both to score and to defend against other robots. Defense is a viable strategy in robotics in first. Depending on the game, defense can actually win you a lot of games. It can do really well. Also depending on your driver and depending on your strategy. So if you have a fast drive base that's very maneuverable and can push hard, then defense may be a viable strategy, right? And you can design around that as you're designing. So all drive bases, right, they have disadvantages and advantages, but they're all task-based. So we'll get to that, what that means specifically in the future. So, right, almost any design can be used in a game, but some designs are more conventionally incorporated than others. Like I was saying, drive bases and climbers are quite common, right? So many mechanism types exist. So what we're just trying to do in this presentation is just to clarify some of the more commonly used ones, all right? Some of the more useful ones. So first we have drivetrains, which a drive base, and now a drivetrain, the way I consider it, a drivetrain is the moving parts in a drive base, and the chassis is the structure. So a drivetrain plus a chassis equals a drive base. A chassis is just your structure, right? No moving parts or electronics. A drive base is your motors, gearbox, gears, wheels, chains, and sprockets. Or not a drive base, a drivetrain. That's your drivetrain. So right when you take your chassis, which is this, your metal drive base frame, so you take your chassis and you put your drivetrain in it, and that gives you a drive base. That's the way I consider it, at least. Other people consider it different ways, but I think that's the most clear way to put it, at least for our purposes today. So yeah, drive bases are super important, especially for certain games which have more all-terrain fields, or maybe they have bigger fields or longer fields, so you can drive more quickly, or you have to drive more quickly in order to cycle faster, or in order to score points on either sides of the field faster. So first we have tank drives, which I've been talking about a little bit, but as you'll see here, basically you have two sets of motors, and they connect to this drive base chassis here. So this is your drivetrain, right? All these components here. This is your chassis, and then this whole thing is your drive base, right? So a tank drive effectively works by having two sides of wheels, and they can operate at different speeds. They're independently controllable, independently actuatable, and because of that, you can turn, right? So if you speed up this side and slow down this side, you can turn. to the right that way. Or you can just drive back and forth straight. What these can't do is strafe right to left. So they can't strafe parallel to the axis of rotation of the wheels, right? They can't move side to side in this direction without first turning 90 degrees, right? Turning 90 degrees, and that takes some time. And then you have to turn back in order to go forward or backwards. So you can really only go in the direction that you're pointing with tank drives. But, strafing isn't super important in many games. So tank drives are a good solution, right? Your most common type of tank drive is going to be your West Coast drive, which features sliding bearing blocks. Here you can see we have a little black thing here. Basically what that does is it's a bearing block, which means that your wheel shaft goes through here and your bearing sits in there. And then this bearing block clamps down onto your chassis. And what this effectively lets you do is slide your wheel back and forth. Only a small amount, but you can slide your wheel in a very controlled way. And what that lets you do is if you have a chain going from this gearbox to this wheel here, if you have a chain going from here to here, right, chains are hard to calculate the distance. And even if you do calculate it right, if you just have a hole there, it's going to really be hard to push that shaft into the hole when your chain is being put on. So what you can do with a West Coast drive with these bearing blocks is you can put the chain on, leave it a little bit loose, and then loosen this bearing block, unclamp it a little bit, and then move it away from the other one. And then that tightens your chain. So you'll get more efficiency in your powertrain. And you can do the same on both sides. So a West Coast drive is just a tank drive with sliding bearing blocks. Now this tank drive has omnidirectional wheels up front, which these can move parallel to the axis of rotation, which allows you to turn more easily, right? Allows you to turn more easily. These do have durability issues, especially over the bumps in the middle of the 2020 field, but Omni wheels are a really good solution for turning. So yeah, and then back here we have traction wheels, which is just plastic tread on a plastic wheel, or it's like rubber tread, and that allows you to just have some good grip, good traction here. And all 6 of these wheels are driven. You can do it with just the back 2 wheels, or even just the middle wheel driven, but having all 6 driven gives you more control and more grip, because surface area on the ground does matter. More wheel, more good, is a pretty common saying. So yeah, usually 6-wheel drives are going to be your tank drives. They can have more or even less. Sometimes you can have a 4-wheel drive tank drive. Now, here we have a 4-wheel drive tank drive, like I was saying, and this has pneumatic wheels, and these are like squishy tires. Now, this was for the 2016 game, First Stronghold, and this 2016 game had a lot of field elements that were super tough, super tricky, super all-terrain. So basically what you had to do was build a robot that can just be rugged and go over everything. So a lot of people actually built treaded, like a tank tread. They built treaded drive bases. This solution is just using squishy pneumatic wheels, right? They're big, these are large in diameter, and there's a lot of them, so you have a lot of surface area contact with the ground. So if like one corner of the robot gets stuck on something, there's a much bigger chance that you're going to be able to extract yourself. But yeah, so pneumatic wheels are good. They're also bouncy, so if your robot catches air, it may not damage as many things. It acts as a bit of a suspension. And now we have another 6-wheel West Coast drive. However, this doesn't utilize bearing blocks, but it does have some sort of sliding chain tensioning mechanism, I believe, although I may be incorrect with that assumption just because I see some belts there. But basically what this does, and what I wanted to show, was a drop center, which basically means that your middle wheel is lower or bigger than the other 2 wheels in the drive base. And that basically allows you to, or that just basically means that only 4 wheels are touching the ground at a time. This also has a drop center, but only with the middle 2 wheels, which allows it to sort of like climb up over stuff more easily, because that way you have, some sort of angle of attack with your front wheels and your rear wheels. So you can have optimal traction at all times. But this drop center allows your wheels to come down a little bit, and you can see they don't need omnidirectional wheels because they have that drop center. So it effectively makes it so that 2 of the wheels at any given time will not be on the ground. Whether you're going forward, you'll tip back a little bit, or if you're going backward, you'll tip forward a little bit. And that'll allow you to turn a little bit better. Generally, the rule for turning is that if a drive base is wider than it is long, it'll be able to turn without, skipping back and forth a little bit. And if it's longer than it is wide, it won't be able to turn unless you do like a drop center or omnidirectional wheels like that. All right, now we go to omnidirectional drivetrains, not to be confused with omni wheels, which are different. Omnidirectional drivetrains allow you to strafe, which is what I was talking about earlier, where you can go sideways, which is pretty useful in some games because it's also really good for defense or for evading defense, right? If you can just drive forward, and then skirt, or like right around to the side, like that's super helpful, right? Because then you can evade other robots, and you can also cycle more quickly. Like maneuverability is speed is one thing, but maneuverability at speed is a really awesome thing. So it's a really good thing to have on a robot. And yeah, swerve is one way to do that. I'll talk about that a little bit more in a second. But omnidirectional drivetrains basically allow you to have more mobility at the cost of complexity. So if you look back here, right, your tank drive is going to be a lot simpler, a lot lighter, probably around 15 pounds for a drive base, which is pretty light. That's pretty light. It's going to be a lot simpler, a lot lighter. Now, if you have your swerve drive here, or any other sort of omnidirectional drivetrain, there are definitely trade-offs, both in cost and complexity. So swerve is the first and most common type of OmniDrive. Basically, what swerve does is uses powered casters. So a caster is a wheel that can rotate, right? It can rotate perpendicular to its axis of rotation. So it can rotate, it can spin, and it can also rotate in this direction, right? So it can rotate this direction and this direction. And that allows it to drive, as well as drive in any direction you want, right? So this robot, these wheels can all turn in this direction, and the robot will go that way, right? So on a swerve module, you have, this is what it's called, a swerve module. You have usually 4 in one robot, although I've seen robots with more, and I've seen robots with fewer. But yeah, so usually you have 4 in one robot, and you have one drive motor. That's this motor. This is West Coast Products, or no, it's Swerve Drive Specialties Mark II module, I believe. They have a Mark III now, which is pretty good. But yeah, so this is their Mark II module, and basically you have a drive motor, which goes to this gear, which goes down to this gear, and then it goes to a bevel gear. If you see here, this wheel here is beveled, or this gear is beveled, so it's a gear on an angle. Basically, it allows you to make a 90-degree turn in your drive. So this motor drives this wheel, and that, because it's, you know, centered, because all this gearing is centered, and then this will orbit around, this wheel can spin, and this motor can still power it. This wheel can spin indefinitely. And then this steering motor basically just goes down to a gear and rotates this whole assembly. And now you have a mechanism drive, or mechanism drive. Nobody knows how to pronounce the word. We're just going to call it a mechanism drive. Mechanism drive for now, right? And what a mechanism wheel does, and what I talked about in the last presentation, is basically it allows you to move something in one direction as you're spinning it. You can also just drive forward, but if you move these in opposing directions, you will drive this way. The problem with mechanism drives is that they're really easy to push, and they're super imprecise. It's because the whole thing is on casters. So if you just go ahead and knock it, give it a push to the side, if you ram into it, it's just going to go skidding off into the distance, which is no fun for the driver, and it really doesn't allow you to score well. So in a game where you have to sort of hold your position and where defense is really important, mechanism drives aren't super useful. And like in games where the robots are smaller and not as heavy with less inertia, mechanism drives are more used just because they're small. They're not super complex, right? You still only have 4 motors, 1 for each wheel, and they can be light. So they're used in leagues like FTC, First Tech Challenge. But also mechanism wheels will have some durability issues if you're running them over bumps and stuff at high speeds. These little rollers can sometimes fall off. And then you have an H drive, which looks exactly like the name suggests, right? You have omnidirectional wheels, each independently powered, and then one in the middle. So when you're driving forward, this doesn't have any problems being in contact with the ground. And then when you want to strafe right to left, it's only one motor powering the strafing, but you're usually not pushing hard to either side when you're strafing. But if you want to strafe right to left, then this will push you in that direction, right? It will push you in that direction, and these motors just kind of chill while you're doing that. H drives are really good on flat fields because, you know, they're pretty maneuverable and they're still pretty complex, or they're not very complex rather. But on fields with bumps, this center wheel can often get caught or stuck, and you'll bend this shaft, that's bad juju. That's no good. So H drives, they have their uses. Team 118 used one on their 2019 robot, and it was very successful. and they have been used in many other cases. But typically for a more all-terrain field, you're going to want swerve, even though it's complicated. Like these modules will probably run you about 400, 500 bucks each. And there are cheaper COTS options out now, and you can always design your own, but swerve is a little bit more complex, a little bit more expensive, but it does have a really good benefit. But enough of that, let's get to our next section. So now we have elevators, and elevators have a use in many, many FRC games, which basically they can be used to elevate or lower a whole robot, or to elevate or lower a mechanism such as an intake. So if your intake is attached to your elevator here, right, and it's down here near the ground, and it picks up something, and then the elevator lifts it up to the height of the goal, whatever that may be. The elevator lifts it up to the height of the goal. Your intake is now converted into an outtake, and then you can sort of spit out the thing you picked up, and then move your thing back down, right? So that's not a very clear, it looked clear in my head, but to you it may not look so clear, so we'll get to the visuals. All right, so an elevator, basically how an elevator works is you have rigging of some sort, so either a chain or a belt or rope, and that's powered by a motor, and it goes through a series of pulleys to raise up your stages. And stages, naming conventions for stages are kind of iffy, but I'm going to go ahead and say that the fixed stage, so this thing here, which is mounted to the robot and does not move, that is called stage 0. So those are your uprights, that's stage 0. And then you have stage 1, which moves up and down. So this is a one-stage elevator, right? So one-stage elevator right here. And basically, I'm glad I didn't conflict myself there because even I forget the naming conventions sometimes. But yeah, so basically how this elevator works is you've got a motor down here, and that motor spins this chain, which goes all the way up, and then this chain is bolted to a fixed place on the first stage, and when this chain spins and this travels up, since this is bolted to it, this also travels up. Now that's not super complex, right? It's just a spinning action. It gets complex if you want more stages, like here in this example where you have, so this is stage 0, this is stage 1, 2, and 3. This is a 3-stage elevator. So now you're going to need some sort of rigging in there so that when you lift up this one, the whole thing is going to lift up. And that gets pretty tricky, but here's a pretty simple diagram of how it works, right? So what you've got, there are two main types of rigging that you can do. We'll start with continuous. So let's start with it in this halfway position, sort of. Here's your motor, right? And then here's some sort of rope, right? Or rope or cable. It goes out from this little spool, right? This is your motor, and then it's on some sort of shaft, like a sprocket or something. Although it probably wouldn't be a sprocket if it's going up and down like this. Although it could be, actually. But yeah, so you've got some sort of sprocket here, and it goes under here, and then it goes up and over this one, and under this one, and up and over this one, and under this pulley, and up and over this pulley, and down to a fixed point on the top. And then you have another one, which comes down from this fixed point and straight back to the spool. So what this does is basically allows you that when you spin your motor this way, and when you make it so that there's less rope here, right? You pull this down, this is going to come up, right? This is going to come up. And then because this is getting shorter, because the whole thing's getting shorter, the distance between this and this is going to shorten, right? So as you pull down on this, this brings this up, and then this shortens and this brings this up, and then this shortens and this brings this up. So that's how it works. And then as you're spinning this way, this is also getting let out and lengthening to compensate. And then when you want to lower it, you just pull the other direction, and this all sort of resets itself. And then since you've got a fixed point here, you're literally just pulling right to your fixed point here. And this is an example of an elevator as used to articulate a mechanism, right? This is an intake of some sort, and this little yellow thing is a ball, like some sort of game piece. And this is your robot drive base. It's a very crude drawing, but it sort of illustrates how it works, right? You've got your intake, and it's going to start down on the ground, and then your elevator is going to raise it up. Elevator is going to raise it up, and then and this little blue thing would slide on this last stage, slide up and down, so it could go all the way down to the ground. The elevator is going to raise it up, and it'll go all the way up, and this is going to give you some pretty good height because this is a 2-stage elevator plus a carriage, which is just something riding inside the final stage is what a carriage is usually described as. Now we have cascading elevators, which are a little bit funkier, and so these continuous elevators, basically when you move them up, they sort of, like, there's not really any specific order to the order in which the stages move up. It kind of just is whatever has the least resistance. Cascading elevators are different. Cascading elevators move up at a constant rate relative to one another. So continuous elevators move, this stage will move up, and then this stage will move up. Or, it'll start with this one, and then this one will move up, and then this one will move up. For cascading, they all move up at the same time at the same rate. So it's going to look something like this. This would not really happen with a continuous elevator. You would have like this stage would be all the way at the top, and then these two would both be at the bottom, right? The carriage and the top stage. Here you have another two-stage elevator with a carriage, and you can see that cascading elevators are a little bit different. So what you've got here, and this is a cascading elevator, although it's kind of like, basically you've just got a fixed point that's moving something up. So this pulley is spinning, and this comes over and attaches down here. So when you spin this, this gets, pulled, and this comes up, and then this lets out some slack in order to compensate. However, as this comes up, this fixed point on this second rope here connects to the top of the stage 0, and so that in turn, as this whole thing moves up, right, this is going to get farther away from here, so this rope is going to take more away from this side, so it's going to bring this one up, right? So each stage brings the next one up, and this one is attached to this stage and to the carriage. So as you spin this, they're all going to move up at a fixed rate to one another. And you don't need to memorize all of this, but it is useful to know if you're making a design. Now, the thing about CAD design and regular design is that ropes and chains and cables are really hard to include. They really are. So it's typically more productive and useful to just make them heavily implied. So leave all the infrastructure like bearings and sprockets and pulleys in place and make it clear, but you don't actually need the rope or the pulley or the belt in there. And we'll get into CAD like that in a little bit. So you can either have elevators that lift your whole robot, which usually need to be stronger, a little bit more overbuilt. This elevator, you can see, is a pretty chunky boy, and it was used to lift our entire robot in 2020, which is about 100, maybe 90 pounds. Not 190, like it's 90 or 100. I believe with a battery it was like 95. But yeah, so this elevator lifts our whole robot, and it's a very simple elevator. If you wanted to be shorter and still reach up to the same height, you would have to add more stages. This elevator is also designed to lift up an entire robot. These look like they're designed more to lift up mechanisms, although these are just mock-ups. But yeah, mechanism elevators have to be much faster, much more controllable, but not as strong as a rule. So yeah, just keep that in mind because elevators are super important, but you only usually need like one on a robot, although sometimes you need more. All right, rotary arms. Rotary arms they're sort of like elevators. They fulfill a similar role in that you can use them to move mechanisms around, right? So they have added degrees of freedom, right? Because they rotate about some sort of axis. So you've got some sort of stick thing that's coming out, and then it's attached to a little shaft. And that shaft rotates, and the sticky stick thing rotates to accompany it. And so that moves whatever's on the end of that sticky stick thing up on a radius, and even behind you if you want, or just up a little bit, or like up and down if you want. So here are some examples of rotary arms, right? And you can use them as a replacement for an elevator, right? So if you want to just lift something up without, having to build an elevator, you can do that in supplement to an elevator, right? So you can have a rotary arm on an elevator. That's pretty gamer to do that, which is shown in 254's 2019 robot. They have this elevator, right? Looks like a one-stage elevator. This is a carriage. That's an example of a carriage. This thing can move up and down and carries their intake, which has spinning wheels here, and the ball comes in there. And the whole thing's on a rotary arm, right? So this rotary arm, you can see here, there's a sprocket, and that sprocket will rotate, and it'll rotate the whole rotary arm. And then it's also connected to a chain here so that this thing will stay level and parallel. And you can also pretty quickly move it, and what they could do is reach behind their robot with their rotary arm, I believe. Actually, no, I don't think they could do that, but feasibly, it's possible to do that with a rotary arm. And now we have CAD for a rotary arm used to store and deposit lemons on our 2020 robot. This CAD is actually not, looks like it's not constrained properly, but the current CAD is. But yeah, so basically what you have here is a shaft attached to a motor, and that shaft has a gear on it, and that gear spins a shaft, or spins this, right, which is on a shaft with a gear. And when those gears spin each other, this second shaft here moves, and because this is all attached to it, this will rotate. So you can get rotary movement that way. Our team is pretty experienced with building rotary arms, and it's one of the things that we like to do frequently. So rotary arms are, they're a simple and effective design, and they work pretty well for a variety of tasks. All right, now we have intakes. And intakes are devices that are used to pick up game pieces, right? So they can be used by the robot. Many varieties exist, right, for different sorts of game pieces and different sorts of games. So here are a few examples, right? And usually intakes, what they use is spinning rollers, right? So you have a roller here, and this is attached to a motor down here. On these three rollers, they spin, and as you drive up to a ball, these rollers spin, and the ball touches the rollers, and sort of the ball gets rolled up into the robot. Here's another example of rollers. These are fixed. These don't. This whole thing sort of moves out. It's actually sort of a rotary arm, although it's pneumatically deployed. But it is a rotary arm, technically speaking. So you have these that spin, and then the balls sort of roll up and into the robot. Here you have a static frame-mounted roller, so it's just mounted to your chassis, and these spin. And as you drive up to balls, there's this frame cutout, right? There's a cutout in your chassis, so you can get those balls into your robot without having to have something that comes up over your bumper here. You can just have them come through your bumper. But these rollers spin, and there's another roller in here spinning the opposite direction, and they sort of just act as you drive into balls. They just sort of slurp them in. They intake them, right? Because the wheels are spinning, and the surface of the wheel the surface of the roller, when it contacts a ball, it'll make that ball move forward, right? So it's spinning, and it moves forward. Now you have a pneumatically actuated intake. So this is more of like a finger, like a grabber. So this is not using wheels. Basically what it's using is just little things that are pushed and they come out. So that's a little bit more unconventional to use, and you can't really see it super well in this image that I have here. But basically what pneumatically deployed and pneumatically actuated intakes, so this is actually on a rotary arm here. But this whole thing, it's got like a little set of fingers or jaws or something that goes in the inside of this hatch panel here. It was a game pieces in 2019 that you had to put, they had Velcro, you could stick them on in there. But you had a little thingy, and it would click, the pneumatics would open up the little jaws, and they would, insert into the middle here, right? They would insert into the middle, and they would open up. I've also seen Velcro and suction cups used on intakes. And that's, not an ineffective strategy. It actually works pretty well. But it just depends on the game and how confident you are in your ability to consistently have this mechanism work and fulfill its task. Now we have indexers, which are devices that are used to sort game pieces, right? Which are usually placed in between an intake and an outtake. So they're not relevant for all games, but they're really important, really vital even in some. So here's an example of an indexer, right? It's on 319's Robot CAD, and we'll look through their CAD in a little bit just to get examples of these. But indexers feed into outtakes, right, which we'll get into in a second. But basically, your intake intakes the ball, and then you just have a pile of balls. You could hold 5 in 2020. Have a pile of balls in your robot. So what do? You have to have some sort of way to get them into some sort of neat, organized line so that they can be used by the robot. Here, in this case, it's a shooter with spinning wheels that shoots the robot out, or shoots the balls out. So you have sorters and you have conveyors. Sorters basically sort things into like a neat, tidy stack. Conveyors basically move things in that neat, tidy stack. So here's a picture of 319's ball pathing system, which I think elegantly uses both of these methods to sort their balls, to sort their lemons. All right, now you have outtakes, and this is going to be our final section here. Outtakes have to be designed to adapt to the game and its tasks. So a lot of kinds exist, right? In 2020 here, you have to shoot balls into the upper port. There's also a lower port you can use, but most people do the upper port. So here you have spinning wheels and a hood, right? A back plate of some sort. So as the ball comes into contact with these spinning wheels, it moves forward, and this hood makes it come off on an angle. That way it'll fly on a trajectory and go right into the goal there, right? It'll go right into the goal there. And now you have here, this is Team 319. Team 2910, Jack and the Bot, they have a hybrid intake and outtake, right? So it's mounted on a rotary arm, and they would pick up the big orange kickball from 2019. There were 2 game pieces in 2019. The big orange kickball was one, the hatch panels were the other. They would pick up the big orange kickball using these spinning wheels here, and then they would have their rotary arm raise this whole thing up, converting it into an outtake, and then they would spin these wheels, start them up real fast, and the kickball would sort of shoot out like a few inches into the goal, right? And then here you have Team 118's pneumatic catapult from 2016, and this was like a little stone thing. It was super low profile, and you would roll the ball onto it, and the pneumatics would, use the compressed air to shoot this thing up, and it would shoot it into the goal on a pretty consistent trajectory because of the backstops in here. So yeah, Outtakes basically just convert game pieces into points. Usually they use spinning wheels of some sort, and there are many different kinds depending on the game piece and where the game piece needs to go. All right, so in conclusion, right, mechanisms are task-based, right? So each has a use in gameplay, right? When you're designing mechanisms, you have to make sure that they will be used and are usable in gameplay. So that means that they're efficient, fast, easy to use, and can work consistently. Many mechanism types exist, right? So this presentation is sort of just aimed to clarify many of the more commonly used or useful ones, because when you're designing robots, you really are going to be using a lot of things that are already have been designed. So knowing those, right, helps you, knowing what research is already in existence helps you improve things a little bit more effectively. So, right, don't try to reinvent the wheel when you're designing. Just improve on existing concepts and designs, right, that have already been proven to work, and that'll let you accomplish game tasks really effectively and also cheaply as possible. So then, the mechanism styles I presented, just sort of use these as a base, right, upon which to build your future designs. So don't copy them verbatim, right? Just sort of use them as a baseline, use them as a guide. Some of these concepts are really, really applicable, and they're pretty easy to implement in different sort of styles. So yeah. All right. So we're not actually going to go ahead and do this activity. I feel like we've run a little long with this video already. But basically what you need to know, 319's robot has an intake, they have a climber, and they have an indexer, and they have a shooter, and they also have a drive base, of course. I'll go back to an image of the robot. Right, they have this intake here, which looks a little bit similar to this intake on the Robonauts robot, and that's because it's from the same game. This intake has spinning wheels that intake the lemons, and then this indexer this indexer moves the lemons into a neat and tidy line to get to their shooter, right? And their shooter looks like this, and then they have this drive base, which is a 6-wheel drive, tank drive. It's actually a West Coast drive. And they do have a drop center on there just by using a bigger wheel in the center. And then they also have elevators, right? These are two nested climbers next to their indexer. Overall, it's a really pretty CAD, and it's a really good example of, it's a really pretty CAD model. It's a good example of how these different mechanism types are used practically on a robot. All right, yeah, so, right there, each mechanism is used to fulfill a task, which your task is based on what strategies, your strategy is based on what task you want to try to do, right? So compared to, some games you want to do a lot of tasks. Like in 2020, there's a lot of different tasks. Like you want to be able to pick up balls, shoot balls, climb, drive, maybe fit under the trench, maybe try to spin the wheel of fortune. There's many different tasks. In other games, there aren't as many tasks. But usually there's around 5 that you have to pick from, and picking which ones are most valuable, because you can't really do them all unless you have, a ton of resources and money and funding and time, which time is it's the only thing that you can't really change, because the build season is pretty constrained at 3 to 4 weeks. But yeah, so, right, unless you have unlimited money and time, you have to pick and choose, and that picking and choosing is what wins games. If you can have a strategy that works, if your design's able to fulfill that strategy, then you will do well, right, if you have a strategy that works well. All right, that's going to be it for today. So thank you all for watching again. Next time we'll be getting into CAD. Actually, this is the conclusion of our design philosophy unit for robotics for first. But we will be getting into some practical task-based design in the future a little bit, and you guys will actually be doing some, and I will be following along with you. I will be doing some as well. So yeah. Thank you all for watching, and I'll see you all next time. Bye.